my colleague who is in charge of the display and the interface of this project. And Makao Ramesh, and my name is Richardson, and we're in charge of the algorithms and calculation behind this project. So when we first got this project, we had no idea what we were doing. So in the beginning, we were told to develop a toolkit for this MATLAB, MATLAB toolkit for this Ionosphere model, which is produced by 72. And what Ionosphere is an upper atmosphere which populated with ions like N plus, O plus, and H plus, all different ions. These ions are affected by magnetic drifts and solar flares and all different other things. So what 72 allows researchers to do is to tweak these variables and produce this Ionosphere model. And these models, these raw data are hard to use. They are just numbers. We got a file and file of numbers. And they are just raw data. They are not really formatted in what we usually use is atmosphere, altitude, latitude, and longitude. Instead, they are organized with flux tubes and number of points on the flux tubes. And second of all, it's hard to visualize. They are just numbers. And third of all, to produce mass amount of flux tubes, they take overnight. So we see these problems, and we develop toolkits to solve these problems. Now, first of all, we input this raw data into our program, and then we interpret it. It's a two-stage interpolation. So now we got a data tube which is uniform. So now the data is in latitude and the altitude. So with this data tube, we can create these displays with one location what the atmosphere looks like, and with a different location what the atmosphere looks like. And also, you can see the progress of this atmosphere change throughout times, throughout different time or in different places. So after I just put it together, design a friendly and simple user interface, and we got our final project. So, well, you might say that why we care about these ions? Well, what the researcher is trying to do is, when you know how the ionosphere works, you can see that how much the satellite drifts in these different ion changes. And also, this ion, the rapid ion change may affect the GPS signal that in the latitude that guides planes. And also, when you try to bounce a signal, a radio signal, through the ionosphere, how much disturbance you can get. So when we know how the ionosphere works, in the end we can know that when it's going to happen, and how long it's going to last. Thank you for your time. Is there any questions?
So I'm looking at your picture on the bottom.
Yes.
The world seems to be flipped. I see the continents a little bit. All the colors in the image, do they indicate that ionosphere is just centered around the equator, or
actually,
what does it show?
For this one, since we are looking at one level of the things, and we're only given certain run of semi, we didn't give many runs of semi. Each semi produce a different model of it. So these are just one flux tube. So one flux tube looks like this. So to produce more flux tubes, it's going to take longer for semi to run. So in the end, that's what it looks like for one flux tube. And that's one of the data that we were getting.
Okay, so ionosphere is everywhere around the Earth.
Right, the ionosphere is everywhere around the Earth. But how the semi calculated is that it's calculated around the flux tubes. So each flux tube is each flux tube actually give you a different, different content of the ionosphere.
If you can explain, what's a flux tube? Is that like?
Oh, that's the magnetic flux tube of the Earth, which goes from the negative magnetic end to the positive magnetic end. And this actually is one narrow.
The problem is, if you imagine the Earth is like this, most people will imagine magnetic flux tubes go like this, but actually there are even some that come off, let's say, hands like this, that'll come right here, like that, right? So that's a smaller latitude range, and that's why the flux that we have here is just that small range of the curve. But if we were to use the model to generate a wider range of flux tubes, then you can get a wider field.
And you have data for different altitude?
Yes, we have different for different altitude, different latitude, and different longitude. What we hear is local time. And one of the things that research really pay attention on is around the equators, that's where the ion actually moves the most. So let's say that we have the GPS in the US actually don't feel much disturbance because the ionosphere actually don't change much around US regions, which, as you can see, the Middle East and Africa, those regions actually atmosphere shift a lot.
Why is that?
Well, because they're affected the most by the electric fields and stuff generated by the sun.
Right.
So, as
It's
the end
like
of the day,
the time of day.
exactly, yes.
It's time of the day too.
Actually, our program, you can even view a movie mode, if you will, that shows the change in ionosphere throughout the day.
You know, so some of these layers of the ionosphere, they disappear during the course of day, right? F layer, H layer, stuff like that.
Yes.
Yeah, the ions change height, change direction, and all that stuff. And that can really affect GPS outages and things like that. So the idea here is if we can generate an accurate model, we can get an accurate space weather prediction, and eventually predict accurately.
So in the end, what program can achieve is now we have a uniform data cube, and then we have a display for researchers to see, and we shorten the time. So now you can only generate like 2 flux tubes, well, not really 2 flux tubes, but around 5 to 10 flux tubes, and get the result of about 200 flux tubes. So you shorten the time that you can do as every day.
The higher the resolution the flux tubes used in the model generate, the higher resolution your image will be in the data cube, the ionosphere trying to convert. But that takes a really long time. So if we can use the same model to generate a few flux tubes and use our program to do interpolation techniques and figure out what's going on between those flux tubes without having to actually generate it, it's a huge time saver.
Yes.
Did you handle any conditions with noise when you went with your interpolation? Because lots of times when you have noise, you're trying to interpolate between the data with noise. That becomes difficult. So kind of noise reduction.
Well, these aren't measured.
These are, yes.
These are model generated.
Right. These are not actual data. These are just what you tweak with 72, and 72 just say, here is an ionosphere model that with the parameters that you entered. So it's not an actual real ionosphere model. It's
Have you tried to take your model and use measured data?
Well, the issue
actually,
is
that's what the research is trying to do now.
Right.
I see.
Because the model itself is not yet accurate because we don't know what the input parameters are supposed to be.
Okay.
So we're trying to, we know what the ionosphere looks like so we can measure it. So we're trying to reverse it and figure out what the drivers are. And then that's when that sort of thing comes in. That's not so hard.
Do you have a question?